Let's discuss USACO's silver problem number one, social distancing. So Farmer John has a farm that's the size of from point 0 all the way to 10 to the power of 18. And what he's trying to do is socially distance each cow to the maximum length. And the thing is, he has grassy areas like here and grassy areas like here. So the reason why he's socially distancing every cow is because he's afraid they're gonna contract a virus, and he doesn't want them to get this sick. And he can only place these cows in grassy areas. For instance, let's say he wants to place a cow right here. So cow one, cow two, right here, cow three. You see how they're distanced in an optimal position where they're not as close as they can be. They're the maximum distance. However, this is just a part of the problem we need to solve for. What we're really looking for is the smallest distance between the cows, so the minimum distance from the optimally distant cows. So we want to solve for d here, d distance, which is minimum distance. To show this is realize how this white line looks shorter than this red line over here. So that's smaller. So we don't care about this distance for this red line. We only care about the white line distance. So I want to repeat again. We're looking for the minimum distance of optimally distant cows. And as an example, I'm going to talk about the sample input we're given. So we're given a sample input where we have 5, 3, 0, 2, 4, 7, and 9, 9. Let's talk about the first line. So the first line tells us the cows. So N is represented as cows. And then M is represented by grassy areas that we have. And let's talk about the rest of these lines. So for the next M lines, we're given grassy area intervals. So let's look at the first interval and try to map it down. For right now, I'm going to erase our example up here. And let's try to map this out. For now, we're going to ignore 10 to the power of 18. And we're going to set the first grassy interval where it's 0 through 2. So 0, 1, 2. So this here is a grassy interval. The 0 represents the starting point, and the 2 represents the end point for the grassy area. Now let's look for the next grassy interval, which is 4, 7. So 3, 4, 5, 6, 7. And then let's look for the next grassy area. This one is a lot different. Notice how our start point and our end point are at the same point. They overlap. So what does that mean? That means we have a really small grassy area where we can only fit a single cow. And now that we've noted down all our grassy areas, we see that there's nothing after the last interval from 9 all the way to 10 to the power of 18. That's a lot of space we don't care about. So when we're trying to solve this problem, we only care about the start interval for the first grassy area, and the last interval for the last grassy area. So we only care about 0 through 9. So only care about 0 through 9. The rest is useless to us. So we can go ahead and just erase this and just focus on this area here. Now that we have noted down where every grassy area is on the input file, now we have to talk about what is the minimum and maximum spacing we can give the cows, given in the area of 0 through 9. Now, let's talk about the minimum we can space them out. A minimum would always equal 1. So minimum distance will always equal 1 for the spacing of the cows. The maximum distance in a situation where let's say this whole area is a grassy area would be equally distant cows, which can be broken down as the last interval minus first interval divided by cows minus 1. Now this minus 1 is pretty important. The reason why is because we can place a cow on a single grassy point. Therefore, we need a minus 1 to equally distance them out. That's something to consider. Let me just move this over. So our result is between equally distant cows and at the bare minimum is at a 1. So that's something we need to consider. Now, to solve this problem, we're going to first solve the equally distant cows equation. So this is equal to, so this is equal 9 minus 0 divided by 5 minus 1. And that's 9 divided by 4 is equal to 2.25. However, in the problem, we cannot place cows on decimal float values. So we need to round it down to 2. Now let's visualize how that's going to look like in an optimal scenario. So we have 0 here, we have 9 here. So let's break these cows into minimum distances of 2. So we can place down a cow here, cow 1. We can place it down here, cow 2. We can place a cow here, cow 3, 4. We can place a cow here, cow 4, 6, and a cow here, cow 5, 8. Because we had to round down, we didn't reach the maximum number of 9. However, we only care about the result of the minimum distance. Even if we placed cow 5 at 9, our result is still going to be a minimum distance of 2. So that's how we can visualize these equally distant cows. So that's the most optimal solution we'll ever get in every instance of solving this problem. So as I said before, the result is at least 1, between 1 and equally distant cows. So between 1 through 2 for this problem. Now let's try to figure out if we can place a cow where we were talking about at equally distant cows. So let's place a cow down at cow 1, cow 2 here. And let's think about this in terms of programming. So we're going to iterate through each grassy area that we have listed. And then we're going to see if we can place down a cow using the minimum distance. So this was a minimum distance of 2. So it worked out for us. So now let's move over to and see if it's in a grassy area. And it was. So we can place down cal 3 here. And then let's add the minimum distance, which is cal 4 at position 6. That works out. However, if we move over to and try to place down cal 5, that will not work. So in our program, we need to figure out if cal 5 is not in the grassy area that we're looking at, then we're going to move over to the closest grassy area we're currently looking at. So it would be at 9, like we talked about earlier. So this doesn't really affect our results, places it down in the optimal spot. However, we only care about the minimum distance and if it satisfies that condition. In this instance, it did. The minimum distances between the cows was 2, a distance of 2. And that concludes our solution. Now, I do want to note that the grassy area intervals that were given were already sorted. However, in most cases, it won't be sorted, so we should sort this. So we can always figure out what's the last interval and the first interval of our grassy area. Also, I would like to talk about how we got it in the first try on equally distant cows. So this won't always work out. We're gonna have another example where it won't work out in the first iteration, in the first attempt, and we're gonna talk about the approach on creating an algorithm to quickly find out the minimum distance. Okay, now let's imagine we have a better example where the intervals are not sorted and we don't get the result on the first try. So if the intervals aren't sorted, we need to sort them first. So we can look at the grassy area one by one. You can also sort this in backwards order. However, most cases we read left to right in ascending order. Now, in this specific input, these specific inputs where n is equal to 5, m is equal to 3, best case scenario, we have equally distant cows in this entire range here, 0 through 21, which is pretty big, divided by the number of cows -1. This -1 just means we can place a cal on a single point. You can go ahead and break that out into separate parts and you'll see it will work. And once we get 5.2.5, we got to round it down. Now, the first intuitive approach is to try to test this best case scenario first. So distancing each cal by 5. So normally I start from the left, but let's start from right. So we have the first cal goes here, and then we jump 1, 2, 3, 4, 5, and then that's the second cal, and then we can place the third cal here, and then the fourth cal here. That's with a minimum distance of the best case scenario of 5. So we saw that with that minimum distance, this doesn't work out. It's impossible to do it with a minimum distance of 5. So we would decrement the second iteration. So it'd be 1, 2, 3, 4. And it could also be right here actually. But same case, this is not going to fit. So with the minimum distance of 4, this will not fit simply because of these areas. Now, we would decrement yet again and again and again until we get to 2. So let's say we want to place a cal down here, cal 1, cal 2. So this is a space of 2. This is quite big. And then cal 3 would go here, and then cal 4, and then cal 5. And we see that minimum distance of 2 works for this case. And if we look in a different order, so let's say from left to right, we would get a cal here, and then a cal doesn't land on the grassy area, right? So we're going to move all the way over here to this first grassy area. And in programming, we're going to shift back that minimum distance of 2, start from there, and then use a while loop to maximize our distance or amount of cal placements in one grassy area, but looks like it's not going to work here. So we're going to do that once again. So if we place this here, it's not in a grassy area. So we're going to start from around here. So the next grassy area minus that minimum distance. And then we're going to use a while loop to continuously check the previous cal location plus that minimum distance. So there's a placement here, here, and let me erase this actually because this part is confusing. Here. And that completes 1, 2, 3, 4, 5 cals. So this is basically the possible location it can land in. We're basically iteratively checking the previous cal location plus the minimum distance. And that's how we can check in terms of programming. Now, although the intuitive approach of decrementing from the base case scenario is what you first think of, we can further increase the speed of this by using binary search on multiple answers. So as you can see, we have a worst case and a best case scenario that can be represented as a left number, or we can call this the low number. And then the right is equal to the best case, or we can call this the high number. And what we can do in a binary search is continually test these values. So I'm just going to give you the answer right away that 1 and 2 do fit these answers of minimum distance that works in these grassy intervals. However, 2 is the most optimal. Once we hit a 3, that's when it doesn't work out. So we continually check multiple answers. So let's say these are all the possible solutions. However, 2 is the one that works. So I'm just going to highlight this in green. And notice everything past 2 is going to return a false whether if this minimum distance fits on these grassy areas. However, 1 would also return true. So there's multiple answers. However, we can identify the most optimal solution for us, which is 2, by incrementing the left or low pointer and decrementing the right and high pointer until we get to a convergence of 2. And that's how we can figure out the most optimal solution in O log n time. instead of ov n time, where we decrement from the best case scenario. Now, let's start coding our social distancing problem. We're converting our ideas to actual code. What I talked about earlier is basically using a binary search on multiple answers method to solve this problem in optimal time. So, in the problem, we need to read the input file. And the name of the input file is SOC dist to represent social distancing input. And we're going to read it. Specifically, the first line is going to be N and M. Now, for the next M lines, we're reading these intervals, these pairs, and we can best represent that using a two-dimensional array. So I'm going to go ahead and call this intervals, and I'm going to use, we're going to append to it. And I should emphasize what N and M mean. N is equal to cows, while M is equal to grassy areas. So this is really just grassy areas and M. And we can break each line into two parts, start and end. So we map this out as integers. Now we're going to append to it the start and end. For right now, we can use parentheses, but I want to use a two-dimensional array. So this is basically a list within a list. I am going to print this out and see what we get. So we run this. And by the way, this is in Python, obviously. We're going to do it in C++ and Java later. So great. Now we represented this sample input right above here. Actually on the right as well, we can see it. And this is where we're going to output our result later as 0, 2, 4, 7, and 9, 9. The reason why we're going to sort in a bit is because our sample input isn't a guaranteed sorted input. And we want to read the first interval and the last interval in a bit. It's going to be really useful for binary search. So we sort so we can read the location of each grass area or grassy area chronologically. So for Python, we can just use intervals.sort. We can sort by the first element if we want to, since there's no overlap in the sample inputs as indicated above. However, the sort is good enough for me. I'm not going to overcomplicate it. This is a silver problem. We can make this more efficient later, let's say in a platinum problem, in a gold division problem. That'll be it. Now, we want to start using a binary search, right? To test out multiple answers. So instead of incrementing or decrementing, from the best case, we can use binary search to cut that down by a significant margin, going from a time complexity of O of n to O of log n. However, we're basically testing out a function that we're later going to call possible placement to simplify our binary search problem. And possible placement just tests out the minimum distance, and we'll discuss this in a bit. So I'm going to put pass, and let's discuss the range of our result. So our result is at the bare minimum a 1 between a cow. So the minimum distance, bare minimum, worst case scenario, it's a 1. And it's between equally distant cows. And we need to represent these with a left pointer and a right pointer for our binary search. I'm going to call this low as our 1. And our high number, our equally distant cows, is, let me print this out so I can show you. It's going to be this last interval and this first interval. We're going to use this. So we can call this by saying intervals. So the last point is going to be -1 and 1 minus intervals 0, 0 divided by the cows, which is n minus 1. And don't forget to use parentheses on here. So we do the subtraction first. So this is equally distant cows. So let me emphasize, worst case is equal to 1. Best case is equal to equally distant cows, assuming from the last point to the first point. Now we can initialize the binary search algorithm by having low not surpass high. So we eventually converge to a middle point. So we need to define a middle point. which can be represented as, I don't need to use int for Python, so mid is equal to low plus high plus 1 divided by 2. This plus 1 just indicates, and by the way, this minus 1 as well, just indicates that we can place a cal in a single point, such as 9, 9. If we can't place a cal in a single point, then we can remove this 1. Now, as I mentioned earlier, I talked about using possible placement to test out the minimum distance and return a true if it fits in the grassy areas or a false if it doesn't. So if min distance does not fit, we could also just say mid as well. Let's say if it does fit, actually. If min distance does fit in grassy areas, we update low. We update it by putting it at mid, and we're not putting +1 because we know this works right here. However, for the else case, we are gonna decrement a -1 here. By the way, to converge, we need high to decrement and low to increment. That's how we can converge. However, this is important here. We don't put a +1, or else it just gets rid of that minimum distance that works in our favor. We want to get rid of all the minimum distances that don't fit in our favor and end up with a single value into one converging point where it goes from a true to a false. So as I earlier talked about in the last example, we went from a true minimum distance of 2 to a false minimum distance of 3, and we ended up with a 2, which would be low. So that means we're going to write low, which is the minimum distance of optimally distant cals, to our output file. For right now, we're going to print that out. So the last value should be low. That's what we're going to return once we break out and converge out of this binary search. I also want to emphasize it's basically converging to a max minimum distance that works. And this is how we can check with the possible placement, and we'll start working on our possible placement algorithm. So let me space this out and delete this print statement. So this is the first part, reading into the input file, then sorting, and then our binary search is down here, this section here. However, for this definition, this function, I mean, we are maximizing each cal placement in each grassy area using given minimum distance. The way I explain that is using first a for loop to iterate through each interval or each grassy area interval, and then using a while loop using the previous cal location plus the minimum distance to maximize that cal placement in that grassy area. So first we need to start with a value called, or yeah, it's an integer value basically, which is cal location. So this is what we're going to use constantly, previous cal location. And we could start that by how I talked about earlier, by grabbing the first point, which is always going to be the literal first point of our grassy intervals. So it's 0. So intervals 0, 0 minus the minimum distance. So we're one jump away, and I'll discuss that in a bit. And we're going to use a cals counter. Cals count. This is equal to n. So let's iterate through each interval. And specifically, we can actually use start and end point. So let's start for right now with the while loop. So while the start is less than or equal to the previous cal location plus the minimum distance, which is also less than or equal to the end, we can decrement that cal's counter. However, as we decrement that, we need to increment our previous cal location with that minimum distance. So please refer back to the video where you can visually see this. This is basically maximizing each cal in each grassy area. This is the main part of the problem. But using the intervals to jump instead of incrementing one by one until you find an interval that intersects is a lot better. However, we also need an if statement. So this if statement is if the previous cal location plus that minimum distance ends up being outside of a grassy area, so the start of the current grassy area, we need to update previous cal location by the start minus minimum distance, which I want to emphasize is the current start interval that we're looking at. However, I'm just naming it start. So if cal cannot, if cal cannot be placed in grassy area interval, we move to the next. Or let's say move to current. Hold on, let me think about that. Yes, move to current grassy area. This might be a little bit confusing. It's technically next, but we're moving right before and then jumping. Just refer back to the example previously given. After we tried to place every cows counter, we want to return whether the cows counter is equal to 0 because we're decrementing. If all the cows are placed, it will equal to 0. This is basically remaining cows left. So it should be 0 once we used up all the cows in every grassy area using this minimum distance. So let's check this one more time. We read the input file, we sort, we use a function to be later used in the binary search. And then once we break out the binary search, we print our result, which should be low, given these converging factors. And I made a mistake. So in Python, we need to do double division. Let's run it one more time. And there's another mistake. So I found the mistake. We just need to round down this answer. We had a float value right before. So I use int and we get 2. That is the answer we are looking for. So let's actually write this down to our output file. We can use low, then file is equal to open, then the name of the file. And we are writing to it. We get 2 right here. Great. Now, I did forget to check an edge case. Specifically, it was this. I had this at equals to 0. However, in this possible placement, it is possible to place more than n cows, so it can go into negatives just for this function. So we can fix this by either using less than or equal to. That's the simplest approach. Or using an and here. And cows count is greater than 0. However, for right now, I'm just going to take the simple approach. So it still outputs as 2 once we run it. Yep, so it still outputs a 2. We covered a slight issue with the possible placement. Now let's go ahead and run this on the web. So we're here now on the social distancing problem. So we're going to go and submit a Python 3.6.9 file, see if it works. Great, this works. So we passed all the test cases, and that's how we can solve it in Python. Okay, now that we've saw that all our test cases passed, I want to discuss the time and space complexity. So it's pretty long. I have it up here, the time complexity, and let's walk through it real quick. So we are iterating in O of m here, range of grassy areas, which is m. Then we're sorting. Normally a sort is n log n time complexity. Specifically in this problem, it's m log m for sorting. Then we go down here, and we actually have a different distance here. I like to call it d, or max distance. We're not using the length of intervals in this binary search. I have a modified version of this, so I'm calling that d. So a binary search is log d for this area. However, inside of our program, we are essentially iterating from the range of the first point of the intervals and the last point of the intervals. So by the end of it, we get this, or a better representation is this, n plus m log max distance, or you could separate these two. Now, in terms of memory complexity, we used O of m to store intervals. And here I'm explaining where n is the number of cows, m is the number of intervals, and d is the range of the minimum distance we've solved for. Now, I did do a couple of optimizations after I submitted the problem. Specifically, when I have placed all the cows that I need to, I basically break out of this function. I return a true or a false. This is my final solution for my social distancing problem in Python. So let's start to solve the USACO social distancing problem in Java. Now, I have the name of this file as solution. So for right now, I'm going to call it public class solution. And let me capitalize this. I just want to test out my code real quick, my file specifically. Okay, so I created my file successfully, no issues. Now we have to start by grabbing the inputs from the sample input. So I'm going to use buffered reader and file reader. So our first line we're going to read demonstrates n is equal to number of cows and m is equal to number of grassy area intervals, right? And we know by the size of n up here, it's up to 10 to the power 5, which is less than an integer data type size, and m is the same. So we know it's going to be an integer. So I'm going to emphasize it's an integer, and we're parsing the integer. And earlier I was talking about creating a function and my explanation, my visual explanation. So I'm not going to initialize int here. I'm actually going to initialize it within our class so it can be accessible to all methods and even our main. We could call it private static int. We're doing n and m. I'm going to do the same for m. Now we have to create a 2D array of all the intervals in the next m lines. So this 2D array has a pair, a start point and an end point. I also want to be able to access this in other methods, so I'm going to put it right up here. Now, I want to talk about what data type it's going to be. It's going to be long. The reason for that is, let's look up here. A and B can be 10 to the power of 18. So some element in our 2D array might be 10 to the power of 18, and I need to account for that by using long, the proper data type. So now I'm going to use a for loop to iterate through each line in the input file. So I want to emphasize the 0th index inside of the current interval is going to be our start point. So let me write a comment for that start point right here. I'm going to do the same, well, almost the same. I'm going to call the endpoint with the index 1. You'll see it in a bit. So I use 1 here, and it is also a long. So let me emphasize with a comment, this is an endpoint. Then we're going to close our input. We're done reading. Now we're going to sort arrays, or sort 2D array by start points. And we're not sorting the endpoints at all. We don't care about that because there are no overlapping intervals in our sample input as indicated above up here. So how do we sort by that start point in a 2D array? We're going to use arrays.sort, where indicate intervals is our 2D array. And we're going to use the comparator function. So inside of our array, we're just going to focus on that 0th index. So here, basically, as I pointed out earlier, it's our start point. So a bracket 0. Now, the intuitive approach I previously talked about is to find the best case scenario or the best possible case where we have a bunch of grass and we find equally distant counts, then decrement until we find a minimum distance that works. So the max of minimum distance. However, that's pretty tedious. We want to use binary search on multiple answers instead of decrementing, how I just explained. So let's talk about the worst case. Worst case is 1. Best case, as I just said, is equally distant cows in the present grassy area range. So what this means is our result is at least 1 and at most equally distant cows. Now, this looks very familiar from a binary search standpoint. Our worst case could be our low, our best case could be our high. And we're going to use long simply because we could get a position where it's 10 to the power of 18. Let me find, where is that? Yes, A, B could be 10 to the power of 18. So we need to use long. So long is low, it's equal to 1, and then high is equally distant cows. So I'm talking about equally distant cows inside our first, or our last interval, which is here, minus our first interval in our intervals array, as indicated here. Now we're going to divide by n minus 1. And this n minus 1 just means we can place a cow on a single point. So now we can start our binary search where we use a while loop, and we don't want low to surpass high. We want to break out of it because we are converging to a max feasible minimum distance. So let me write that down. Converge to a max feasible min distance. And inside
our binary search, we need to figure out mid. So we need to keep in mind that we want the number to fit in the data type. So normally we do high plus low divided by 2. However, that's not going to work all the time. So what we could do is we grab low. So let me write that down as a comment. So we grab low plus half distance, and that will give us mid. So how can I represent that? Well, first off, low, just as is. And then inside our half distance, we are essentially doing high minus low divided by 2. That's our half distance. Now, let's talk about our first if statement. I actually want to create a function somewhere else and call it possible placement to simplify our code so we can easily follow this binary search. It's not going to be a nested while loop with a for loop. I want this to be as readable as possible because this is a complex problem. Now, if it is possible to place this minimum distance, we actually want to save this answer. Then try for a larger minimum distance. The way we can represent that in code is low. We move the low pointer to mid, or the low number where mid is. Let me write a comment to emphasize this. So if min distance / mid does fit in grassy areas, we save low and try for a larger min distance. That's what we're essentially doing here. Now, the opposite is the min distance / mid does not fit. So we get rid of incompatible min distance. The way we could do that is moving our high pointer to mid -1. This completely removes it, so -1. However, I want to explain that we could get stuck into an infinite while loop right here. We need to do something about mid. So notice in programming, we round down. Let's say I got like 2.5 when I divided here. We round down to 2, or like 2.99. It gets round down to 2. I want it to round up to high instead. So I don't constantly keep running this if condition over and over and getting stuck in a while loop. So what we could do is just add a 1 here. So the mid distance won't ever overlap with the low pointer. And when I mean pointer, I mean like the number low, high, mid. So after we're done here, we write min distance of optimally distant cows to output file. And remember, we're writing to SOC distance or dist.out. Now, I want to emphasize when we break out of this binary search, our most updated solution would be low, not mid or high, because they're overlapping in some cases. It would be low that would pass this possible placement function as true. I'm going to discuss what we should be putting in that possible placement. This means that this minimum distance fits in our grassy areas. So right up above, I'm going to create a possible placement function. We want to return a Boolean. Our input is actually a long, which is represented as the minimum distance. Usually, well, it's always going to be mid, but mid represents the minimum distance. So I want to re-emphasize. This method is to test if all cows can be placed using a certain minimum distance. Now, I discussed this in our visual explanation that we're using a previous cow location plus the minimum distance to maximize cow placements in each grassy area interval. Now, because of that, we need to initialize previous cow location. And we also need to initialize remaining cows with n. I'm going to discuss what we should be using here in a bit. So instead of incrementing by the minimum distance to our previous cow location, then checking our intervals, we can actually iterate using our grassy area patches instead of going up by 1 each time plus that minimum distance. It's a lot faster. So what we could do is iterate by our interval using a for loop. Now I'm going to rename this just for the sake of simplicity. So our start point is our 0th index of our current interval we're looking at, and our endpoint is equal to the interval indexed 1 in our current interval. Now let's start with the while loop that I discussed in our visual representation. So we essentially want to maximize cow placement in current grassy area. So we use a while loop. and we look at start, and we're going to put something like the cow location here. It's just a placeholder for right now, and then end. Now, earlier I talked about using the previous cow location plus the minimum distance. So we're going to use that here. So previous cow location plus min distance, and we're constantly checking this. Because of this, we want to say that we start with our previous cow location with our absolute first start point, which is 0, 0 in our in our intervals. And since we're adding a minimum distance, we actually need to step one minimum distance back in terms of location for our previous cow location. Then we want to continuously increment this previous cow location. And we actually need to create an and condition here. Just copy and paste this right over here, and they'll fix this error. Now, every time we jump over and see if we could place the cow in the grassy area range, we also want to decrement if it's true. You want to reach 0 eventually. Now, let's say this grassy area, we're able to put as many cows as we want. We need to loop back around to to this start of the for loop. Now we imagine that the previous cow location plus the minimum distance is not in a grassy area range. We need to think of an if statement. We can represent that with this comment here. So if next cow placement falls out of grassy area interval, prepare our cow placement for the while loop right up ahead. So this doesn't get triggered the first time around. However, it can get triggered right after this while loop, that first iteration of the while loop. So we want to look at the previous cow location plus the minimum distance, and we want to make sure it's not less than start. If it's less than start, then we have to update our previous cow location by using the current start of the interval minus the minimum distance, so we can satisfy this condition in this while loop. Now, this will be able to place cows. Then normally we would just put return here, where if the remaining cows is less than or equal to 0, it will return true. If it's not, then it will return false. Now, there is some optimizations we can do to this, such as, let's say we have a bunch of grassy area points, specifically in our first sample input. You see that the minimum distance 1 does fit. However, it lets us place a bunch of remaining cows. That wastes a lot of time. So let's change this. So every time we change remaining cows, we want to create an if statement or if condition, which is essentially this down here. We're just doing it earlier. We don't really care once it hits 0, like it returns true if it's a negative. So we want to return it as soon as possible. So we put this if condition with a return true. And if we're able to get out of this for loop, that means we didn't place enough cows. So it is return false down here. Now let's test this. So we got 2. We'll check the answer in a bit. However, I want to talk about the time and memory complexity of this problem. Specifically, this was our binary search on multiple answers method. So let's break this down one by one. So we iterated an O of m here, the length of m. Then we sorted our intervals of length of m. So that's going to be m log m. So that's our biggest contributor so far. Now this is where it gets a little difficult. We use binary search of the length of d, distance, our minimum distance, our max distance. The reason why I don't say m or n here, it's because we modified our high value. So this is log d, this binary search. However, we also have this possible placement function method where we iterated through intervals in O of m, and we also use the while loop. So the best way to represent this is I'd like to say n log d plus m log m. It discusses our binary search over here, and it discusses our sorting over here. Now, our memory complexity that we used was O of m to store intervals. After that, we're using constant space for numbers like high, low, mid, remaining cows, previous cow location. Now, I want to emphasize this is where n is num of cows, m is num of intervals, and d is range of min distances. I'm going to run it one more time, make sure it compiles correctly. Yes, it has. So we're about to go to the web page and test it out. So now we're on the web page. So I'm going to select Java. Now we're going to submit it. Great, it passed all our test cases here. Now we'll conclude our Java solution. So let's code our social distancing problem into C++. So first off, we need to open our input file. We can use ifstream and soc dist.input.in. We see that we get an error right away, so we need to import or include a couple of libraries. So we're going to include fstream. We're going to use using namespace std. We corrected our error. Now we read the first line. Our first line, we are reading essentially n, which is represented as num of cows, and m as num of grassy area intervals. So we're going to read into the input and assign nmm. Now, I actually want to assign our int n and m as global variables, so I can use them in a function later on. I'll discuss that in a bit. So after we assign n and m, we are going to create a vector of pairs for all the intervals in the next m lines of the input here. So 0, 2, 4, 7, and 9, 9 for this sample input. So we're going to use a for loop and indicate we're iterating through each interval from 0 all the way to m. And that vector is going to be called intervals. I actually want to assign that as a global variable as well. And I want to specifically say it's a vector. And we're going to use a pair to indicate that we only have 2 items in each interval. Now we're getting an error for vectors because we need to include vector here. Great, that worked. Now I want to discuss that a and b could be 0 at the very least and 10 to the power of 18 for each interval. So we want to use long. However, for me, typing down long is too repetitive. We're going to keep seeing that variable, the data type. So I want to say type def long is just ll. And this can be indicated here, data type. This is A and this is B of the pair. Now we can go ahead and assign our interval pairs their numbers by using input like above with n and m. We can use .first to indicate our first item in our pair, which is basically just the start point and the end point, and then .second as our last point. I also want to resize our vector to m, size of m. Now we created a vector, and I want to actually print this out. So this is how we can print it out, and we could see we have 0, 2, 4, 7, 9, 9 in our array. So great, that works out for us. So now after we grabbed all our input, we're going to close our input file. Then we're going to sort. So the reason we're going to sort is because this is really useful when checking if our minimum distance we're looking at plus the previous cow location is going to land on a grassy area. So sorting is going to allow us to chronologically look our input files. Remember, our simple input is not always going to be sorted, so we should sort it. We're going to sort intervals.begin and then .end. And then we're going to include algorithm up here, so we could use the sort function. Now, after we sorted, the intuitive approach is basically to grab the very first interval and then plus minimum distance, check if it lands in a grassy area. If it doesn't, we move to the next grassy area, and so on. And we want to start that minimum distance with the best case scenario. So I'm going to write that down. Best case is actually equally distant cows in the range of grassy areas. Then, as I said, the intuitive approach is to decrement this until we finally arrive to an optimal minimum distance. However, that takes too long. What we could do is also look at our worst case scenario, which is 1. Now, this looks familiar. This looks like a left pointer and a right pointer, where we can search for a minimum distance. We're essentially searching for an optimal distance, specifically where we have a max min distance. So where a possible placement converges from a true to a false. And I'm going to show you how that looks like in a bit. We want to use a binary search on multiple answers. So let's start with low.
which is equal to 1 worst case scenario, and high, which is equal to equally distant cows. Notice that I'm using long. That is because low, high can be A or B up here, which can range all the way up to 10 to the power of 18, which might be too big for integer. Now high, we can describe it by grabbing this last interval minus this first interval divided by n number of cows. How can we describe that in C++? We're going to use intervals and m minus 1 dot second minus intervals 0 first. So remember, this is our endpoint, which in this sample input is 9. This is our first point, which is 0. Now we're going to divide by n. Now, not only do we have to divide by n, we also have to subtract this by 1, specifically because we can place a cow on a single point, just like here at 9, 9, and we need to adjust to place a cow on a single point. Now, as I talked about earlier, we are essentially converging to a max feasible min distance with a binary search. So it's going to look like while low is less than high. Then we want to calculate for the mid distance, which is normally it's low plus high divided by 2. However, this is not going to work for right now. We can have an A and B that is 10 to the power 18, so we need to account for that. What we can do is initialize mid with a different formula where we grab low plus half distance. And the way we can represent half distance is grabbing high minus low, then dividing it by 2. This is half distance. And that's our midpoint. And this is how our mid is going to look like right now. Now, we talked about possible placements earlier. So I'm going to discuss what the if statements are going to be. So if min distance slash mid does fit in grassy areas, we save low and try for a larger min distance. So it's going to look like this. If possible, placement of mid is true, then we're going to update our our low pointer to our mid pointer. So this essentially saves low. So we don't get rid of it necessarily, but we do try for a larger minimum distance. And our else is going to be basically the opposite, where we get rid of high because it wasn't a possible placement. So we use -1 to get rid of that current high. So the best way I can explain this is else min distance slash mid does not fit. We get rid of current high by lowering upper bound. So let's talk about what happens after the binary search on multiple answers. So once this converges, we will write the output. However, I want you to think about how binary search works. So notice the mid distance has a divide by 2, and we are not getting float values here. So let's say we have a 1.5, it would round down to 1, and that can overlap with our low. We don't want that. We can end up in a super loop, an infinite loop. Therefore, to get around that issue, we can add by 1 here and have our midpoint only overlap with the high point with certain scenarios, and our low point will never get stuck. It will converge at a certain point and exit the while loop. Because of that, we write the min distance of optimally distant cows with low to output file. Remember, we're using socdist.out, social distancing.out file. Then we close our output file. And that would conclude the problem. However, now we need to work on possible placement. The reason why I'm making a function out of this is just to simplify this binary search problem. I want to simplify this as much as possible so we don't have a for loop running in this if statement and a while loop. It gets really messy. So right up here, we're going to actually call create the function. So it's a Boolean that we want to output. So it's going to output a true or false. Call this possible placement. And our input is our minimum distance, which is always going to be that mid number in our binary search. What possible placement function does is function to test if all cows can be placed, maintaining a certain min distance. So a way that a lot of people think of possible placement in this scenario is basically to grab a previous cow location, then plus equal min distance, then check if location is in grassy area. If it's not, they just keep adding a 1. Now, this can work. However, incrementing by 1 can take forever, especially if the spaces between these grassy areas are huge. So what we can do instead is take advantage of this sort here and iterate using each interval. We're still going to use previous cal location and check plus equals minimum distance, except we are not including this final part where we're adding 1 to each time. I'll show you in a bit. So we're going to use previous cal location. I'm just going to initialize it like this. And I want to use a cows counter, which is n, right? So I'm checking each time if this is less than or equal to 0 at the end. If the cows counter reaches 0, we return true. If it doesn't, then we weren't able to place all the cows, so we return false. So I'm going to iterate through the interval pairs of long. Now, let's think of where our previous cow location should be. I want to use a while loop where it constantly checks our start point and our endpoint with the previous cow location plus the minimum distance, right? Because of this, I need to start previous cal location minus distance right before if you want to place the first cal. So I need initialize previous cal location with, actually spelled that wrong, intervals 0 dot first, our absolute first point minus our minimum distance. Now we've satisfied this while loop condition on our first try. However, in our while loop, if this is true, if this condition is true, we need to update our previous cal location for our next iteration, and we also need to decrement our cows counter. Now, if we decrement the cows counter and it ends up being less than or equal to 0, this is an automatic return true. We were able to place all cows. Now, in a perfect scenario where, let's say in this sample file, this whole thing from 0 to 9 was a grassy area, this would work. It would eventually break out and return true. Also, I want to say that if we finish this for loop without being able to place all the cows, we were returning false, but that's a separate case. Okay, so let's talk about this while loop. So this will work in an optimal situation where the whole farm is a grassy area. However, let's look at the sample file with a minimum distance of 2. So we were able to place a cow on 0, then on 2, then on 4, then on 6, and then 6 plus 2 is actually 8 and does not land on a 99. So we need to create an if statement that takes advantage of iterating through the intervals. So this if statement is going to be if next cow placement falls out of grassy area interval, prepare cow placement for while loop. So this means we're out of the grassy area for right now. Now we prepare our while loop by grabbing previous cal location and then grabbing the current interval first. So the start point of the current interval minus minimum distance. So it can satisfy the next condition. So instead of incrementing by +1, we can go straight away to that grassy area and place that cow. This fixes the issue of having grassy areas really far apart from each other. We're able to iterate quickly through grassy area placements. I'm just going to leave a comment here emphasizing what the while loop does, which is maximize cal placement in current grassy area. So before I move on, I identified a small problem here. We just need to do this, where we modify our while condition. Now, I actually want to talk about this real quick. This will work. This while condition will work without this whole part over here. However, just to simplify this, to be easy to understand, I'm going to leave it like so. If you want to optimize this, you can delete this. It will still work. And I'm going to run it. We still got 2 here. Great. Now we're going to move to the web page and test out our code. So now we're on the web page. We're going to choose our file. Now I selected our C++ file. We're going to submit. And it passed all our test cases. So in conclusion, I want to talk about how this is a binary search method and our time and space complexity, where n is num of cows, m is num of intervals, and d is the range of min distance answers. So let's break down the problem. Now we iterated through O of m here, where we read our file, and we stored it in intervals
Vector.
using pairs. Then we sorted an m log m here. So that's our biggest contributor so far. Then we used binary search. This is the little tricky part. The range of our possible answers was 1 through equally distant cows. So I'm just going to call this log d. However, we also have a possible placement here where we're iterating through the intervals, and we also have a while loop in here where we're incrementing by min distance. So the best way to represent this is n log d to represent our binary search and our possible placement method, then m log m to represent our sorting. And our memory complexity, it's O of m, where it is intervals, size of intervals. Now I'll conclude our solution in C++. This is my entire solution down here. So this is my entire solution.